This video discusses random variables, and we focus on the continuous type random variables in this video. We know random variables are functions. They are functions from a underlying sample space that map elements in this underlying sample space as to numbers in a set. In this course, we always consider numbers from the real line. For example, there are functions that map to a set of numbers such that those numbers could be, all the numbers in such set can be listed with natural numbers, x1, x2, x3, and keep going. But such set contains no non-empty open intervals or subsets. There is no open intervals in such sets of numbers. And normally we refer to those functions as discrete real-valued random variable. So basically, with probability 1, such discrete random variables will only take numbers in such set C, and such set only contains at most countably many numbers. So you can list all the elements in set C using a set of natural numbers. The support of a discrete random variable is defined by the PMF function, the probability mass function, such that it contains all numbers from the C, and the probability of x takes those numbers need to be strictly larger than 0. Note again, given the definition of discrete random variable, the support of a discrete random variable has empty interior. Basically, it means it contains no open intervals or open subsets at all. Then this leads to the discussion of another type of random variables, continuous random variables, where, we allow random variables, for example, could take any positive values from the open interval. So these are functions that map from a sample space to a set of numbers that could contain non-empty open sets. Next, we're gonna see one example such that we're gonna introduce a random variable that could take all positive values from the real line. So it contains open intervals in the possible values that could be taken by this random variable. We consider this example waiting time. So suppose customers come in according to a Poisson process. The number of arrivals that occur in an interval of length t follows a Poisson distribution with arrival rate lambda t, and what happens in disjoint intervals are independent from each other. So knowing the arrival numbers in the interval 0 to 1 has nothing to do with the number of arrivals in the time interval from 2 to 3. As long as there is no overlapping, they are independent from each other, those random numbers. The question is, how long do we need to wait until the first customer, and what is the distribution of this waiting time? You can pause the video at this moment and try to figure this out yourself. Well, the distribution of the waiting time until the first customer, what is it? Let's denote NT, the number of arrivals within time interval 0t. Then based on the condition given in this example, we know NT follows Poisson distribution with arrival rate lambda times t, because the interval 0 to t is of length t. And now let's denote T1, which is the waiting time until the first arrival. Note that T1 strictly larger than t is equivalent to say that NT equals to 0. So this event means within the interval 0 to t, we do not have the first arrival, right? The waiting time is longer than t. That basically says there is no the number of arrivals within this interval is 0. And if the number of arrivals within this interval 0 to t is 0, apparently we have to wait longer than t, right? So these two events are equivalent to each other. Now, can you proceed from here? You can pause the video and finish the rest yourself. So essentially, the probability of this event, t1 strictly larger than t, is equivalent to is equal to the number of the probability value of nt equal to 0, right? They are essentially the same event. And nt we know follows Poisson distribution with the arrival rate lambda t. We just plug in the PMN function of the Poisson distribution with arrival rate lambda t when we get this result. To describe the distribution of random variables, we only need to specify either CDF, right? This is one way to represent the distribution of a random variable, and the CDF of T1 is essentially ft1t, small t, is equal to the probability value of the event T1 strictly smaller than t or equal to t. And we have already derived the probability value of its complement event. So it's simply 1 minus its complement. This is the CDF function for T1. In this way, we specify the distribution of the waiting time, T1. Note that T1 here can take any non-negative values, right? Any positive values. And its CDF is differentiable, which can be expressed as a Riemann integral. And this value, if you pay attention to this function, is a very smooth function. It's continuous, it's differentiable, and it can be expressed as a Riemann integral of its own first derivative. So we have actually two ways to specify the distribution of T1. The first, of course, is the CDF function. But note that the CDF function can be written as a Riemann integral of this small ft1 function. Here we can choose the small ft1 function as the first derivative of the CDF function. And based on the results we have, you have learned from any integration or integral theory, we know the integral, the Riemann integral of this small f function is essentially equal to this function, right? As long as we integrate from 0 to t. Well, for t equal to any negative values, we simply set this small function to be 0, right? So there are two ways to specify the distribution of T1. We can use the big F function, CDF function. We can also use the small f function, which is called the probability density function, PDF function. And T1 may take any value, t such that ft1t is larger than 0. So basically here, for all positive values, that is possible to be taken by T1 in this example. And why do we call this small f function probability density function? Is actually a quite intuitive name, because if we integrate the density, we get the mass, right? If we integrate the probability density via the Riemann integral here, we get the probability value. However, if we work with Riemann integral, we cannot find such f for any discrete random variables. Right? For example, consider a Bernoulli distribution. We have CDF function in this way, right? It's basically flat almost all the time and has a jump at point 0 and point 0 and point 1. So here is a jump from 0 to half, and then at point 1, it's a jump from half to 1. If you take derivative, well, except for 0 and 1, indeed this function is also differentiable. However, it's almost everywhere is derivative equal to 0, and there is no way to find such a small f function such that where Riemann integral to rewrite fx as a Riemann integral of such small f function. Therefore, we could use this probability density function to define continuous random variable. That is indeed what we do here. So a real valued random variable, a real value random variable x is a continuous random variable if we can find a non-negative function small fx such that the probability of x, random variable x smaller or equal to small x from the real line, or simply, which is simply the CDF function, right, can be rewritten as a Riemann integral of this small f function. If we can find such a small f function, then we say this real value random variable is a continuous type random variable. We know from the integral theory, we can change the value of small f function at points, at most countable many points. So you can change the values of the function at most most countably many points, and the integration remains exactly the same. So there's many candidates of fx satisfying this condition. However, by convention, if we have CDF that is differentiable, we always choose this small f function, right, to be the derivative, first derivative of the CDF function. Now, how do we specify the support of continuous random variable? Oh, again, we use PDF here. So for discrete random variable, we use probability mass function, and here for continuous random variable, we use PDF, probability density function. And this continuous random variable, continuous real values random variable x could take any values, right? The support of x is any value such that the small f function, and normally we choose small f function if fx is differentiable, then we choose small f function to be the first derivative of CDF function. And this support of x contains all the numbers x, such that the small fx is positive at those numbers. Or here, given if we have differentiable CDF, that is equivalent to say that the first derivative of the CDF function takes positive values at those numbers. Those are the numbers in the support. If we look at, if we rethink about the example, right here, the support of a continuous random variable, they have non-empty interior. It contains open intervals. For example, it may contain any values from 0 to infinity, so it contains non-empty open intervals. Those are an continuous random variable x, for example, in the example we have just discussed, could take all values within this open interval. And how many numbers we have here? Well, even in the open interval from 0 to 1, there's already uncountably many possible values that could be taken by this random variable we discussed in the example. So let's compare the discrete random variable together with the continuous random variables. So we know for the definition of both random variables, both types, we use their distribution to specify which are continuous, which are discrete, and to specify their support for the real valued discrete random variable, we use the PMF function, the probability mass function, and for the continuous random variable, we use the PDF function to denote their support. If the real valued discrete random variables only takes numbers of at most only takes values with that at most countably many different values, well, here for continuous random variable, they could take uncountably many different values. From the support, it's also easy to see that the support of a discrete random variable, right, has empty interior. It contains no open intervals at all. For example, it may take values 0, 1, 2, 3, but there is no open intervals contains in the possible values could be taken by a discrete random variables. However, for a continuous random variables, or it can contain non-empty interior, contains open intervals within the support, right? For example, in the example we have discussed, the waiting time can take any values within these open intervals 0 and 1. So this video briefly discusses the definition of continuous real-valued random variable. Hope you enjoyed this video. Thank you for watching.